Solubility and concentration. So solubility is all a function of particle size, largely, and then nature of the solvent and nature of the solute. So the first thing is how big is the particle? And if it's small enough and light enough, it will usually go into solutions, sodium, potassium, things like that. Things that are large and heavy, like carbonate ions, tend to be pretty large, tend to be insoluble. So it's all about how big the particle is. Is it polar or not? Is the particle polar or not? And is the solvent polar or not? All that goes into deciding whether or not something will dissolve. For example, there's a molecule called MTBE. Now, we don't have it anymore, but used to be back in the day, we added this to gasoline. It was a fairly helpful thing. And then we found out that not only is it soluble in gasoline, this molecule right here, but it's also soluble in water, up to 42 grams per liter. So the problem is up here around this oxygen, this makes this end of the molecule slightly polar because this is a bent molecule right here. And with that oxygen sticking out there with its lone pairs, it's slightly soluble. So this thing would actually dissolve in water. Well, why is that a problem, you might ask? It's in gasoline, it's in cars, it's in gas stations. Well, gas stations sometimes leak. Here's a fuel tank at a gas station, and it's evident down there by the puddles at the bottom that you're getting some leakage out of those polypropylene tanks. There are lots and lots of tanks in the whole world that are quite old, and so now we say that this is not something that we want in our gasoline, so it's been actually removed from our gasoline. We've already talked about supersaturated and saturated, and this is an example of that. Here's a lake that has seasonal water input. And so in other words, sometimes you get water in it and then sometimes it just sits there and dries out. And since it's in Death Valley, it's very, very hot and very, very dry. So you can see the water over time leaving behind more and more salt. And what happens is that salt crystallizes out and becomes more like this. And you can see some very, very briny pools, concentrated pools, and then you see a whole lot of salt on the surface. If you've ever been to Utah to the Bonneville Salt Flats, you've got the same thing. You've got a lake that had some salt dissolved in it, Bonneville Lake, back around the time of the dinosaurs. Then at some point, something gave way in Oregon or Washington, I can't remember which, and all that water flooded out to the ocean, so leaving behind an awful lot of salt. They let people come and rake up some of the salt sometimes. That is not a picture of the salt crystals that you get from that lake bed. This is a picture of salt from a cave, actually. You get these very, very beautiful, very, very long crystals. They grow that way over a long period of time. So if it's a very long time that the crystals form, they tend to form these beautiful clusters. Otherwise, they just look like a lot of grain if it happens fast. What can we use our solubility knowledge for? Well, we can look at how to clean things. We can look at how to separate or purify things, and we can look at how to identify things. So the first thing, let's say you get some grease on your hand. What are you going to do? How do you get it off? Well, water and grease don't work, right? They're immiscible. So you want like dissolve like. So to get off something greasy, you have to use something else that's greasy. So conceivably, you could use corn oil or margarine to take off the grease because they're both non-polar. You can use other cleaners as well. Soap is made from a non-polar substance. Water is the universal solvent. And I'll let you read this for yourself. Here are the electrons flowing around, and as you can tell, the electrons spend much more time in the oxygen than they do with the hydrogen. And because of that, you get a polar molecule. Positive near the hydrogens, negative near the oxygen. Here is some water surrounding salt. And when water surrounds salt, it'll pull on those salt ions, the sodium and the chloride. Notice the negative ends are attracted to the positive sodium. The positive ends of water are attracted to the negative end of chloride. And since they're bonded to it, it'll actually pull them apart. And you can see those, that's called dissociation. So that's how things form. The idea that oil repels water isn't so much true as water just doesn't like oil. So water would rather be around itself than around the oil. So you can see that given the chance, the water molecules moving around will actually exclude the oil. On a waxy leaf, leaves have wax on their surface, some of them heavier than others, in order to prevent them from drying out. But you can see that the water forms these little balls on there. It doesn't form an even film because the water molecules would rather hang out together than be around the wax. Same thing on your car. That water skin is what, that surface tension is what water strider bugs use to walk on water. Okay, the water almost forms a thin film of connection between water molecules. Okay, so how do we wash our hands? Okay, well, the molecules in detergents and soaps have a polar end and a non-polar end. The polar end is attracted to water. The non-polar end is attracted to the oil, and so it allows the two to mix. There you go. Oil molecules surrounded by water molecules. Acetone. Some of you may have acetone at home. It's commonly known as fingernail polish remover, the stinky kind. And you can use this acetone for all kinds of things. It'll take off, well, fingernail polish, obviously, but adhesives. If you have greasy stains on things, it'll help take those off. But it's also highly flammable. You can also spray it in something that's got water residue in it. It'll combine with the water and you can pour it out. So if you have a bead of water on the inside of a flask or something, sometimes you can put some acetone in there, swish it around, pour it out. It'll carry the water with it. And then any leftover acetone actually evaporates away. Here's one more non-polar interaction. I hope you can bear it. If we're looking at concentrations of solutions, we can either use approximate terms like we have been saying. We've been saying saturated or unsaturated, or we can actually describe it in terms of numbers. Let's look at solubilities of things, right? So in that book that it mentioned just then, it'll list the solubilities for water, alcohol, ether, acetone, and benzene. Now, we don't really care about most of those. We actually care about water the most. But you can look up these things. They're also on the web. And when you look up something, you can see what the solubility is in water. And we can then go through and actually give numbers to things, right? So we can actually do a mass percent. We've done that before. We've looked at what percent something is sodium, percent composition. You can also do the same thing like a 10% salt solution. So you could take 9 grams of water and 1 gram of salt, and that would give you a 10% salt solution. You can also do mass by volume. So you can do grams per liter, okay, or grams per milliliter. You can do it volume per volume. You can do parts per million. So that's the same thing as like a percent. Percent is parts per 100. Parts per million is, well, parts per million. And most importantly, you can do molarity. Molarity is symbolized by the capital letter M, and it is the number of moles of solute divided by the liter of solution. And that's what we use in lab most of the time. We see a lot of products out there that will say what percent it is. And this is sodium monofluorophosphate, where it's 0.14% weight per volume. So that means grams per milliliter or grams per liter of fluoride ion. And it's just a way of reporting to the consumer how much stuff is in there. Here's another one right here. They're representing how much sodium fluoride there is and how much fluoride ion there is. Okay, and they're required by the government to do that. That way you can make some comparison between those products. You also see it in chemicals that you may use around your house, like bug spray. Okay, so you can look up on the side and it'll tell you what percent those things are. So this is 25% of the actual chemical, 75% inert means like either water or some other solvent. In this case, it's an actual petroleum distillate because it has to be a non-polar solvent for this stuff. You can use this at home along with dimensional analysis. So you could say, in my bottle of Visine, how much glycerin is in this, because it'll tell you what percentage of glycerin it is. And it says it's 0.2%, so that means there's 0.2 grams for every 100 milliliters. And the whole thing is 15 milliliters, so you can figure out how many grams this is. I don't know why you would do this, but it's possible. When you get to alcoholic beverages, some bottles will represent how much alcohol there is, like 10% by volume. So it's mainly water. Other things will represent it in proof, right? So here's a 750 milliliter bottle. It's 53 proof. Well, what unit is proof? Well, proof is just an old term that we don't really have a need for anymore. We just use it because we've always used it. But basically, if it's 53 proof, then it's 27-ish, 26.5% alcohol. The government measures a number of pollutants, things that we have concerns over, in parts per million, parts per thousand, or parts per billion, just depending on what kind of level it reaches before it becomes very, very dangerous. When you see ppm or ppb, what you're saying is parts per million, parts per billion. And you can use this information to calculate stuff if you really, really want to, but realize that parts per million is pretty, pretty small and parts per billion is way smaller. But there are certain chemicals in the air and in the water that we need to be worried about. And it's just like a percentage, but instead of saying like 0.000003%, instead they'd rather say like 30 parts per billion or something like that. It just is an easier way to express it. The one that we need to worry about most in chemistry is molarity. Whenever we look at bottles of chemicals in a chemistry lab, we're going to see the expressed in molarity, not in parts per billion or not in grams per liter or anything like that. And so we need to concentrate on molarity. And how do you calculate that? So how do you calculate molarity? Well, molarity is moles of solute per liter of solution. Not per liter of water, per liter of solution. So, for example, if I need to make 2 liters of a 1.5 molar NaCl solution, how do I make that? Well, if I plug in the numbers I have 1.5 molar. I don't have moles. I do have 2 liters of solution. How do I find moles? Well, all I'd have to do is multiply, right? So what's 1.5 times 2? 1.5 times 2 is 3. So I would need 3.0 moles. Now, moles of what? That's moles of solute, which is NaCl. How much does 3 moles weigh? Well, 3 moles times, let's see, sodium's 23, chlorine's 35, so just rough guesstimate is there's 58 grams per 1 mole. So what is that total? 3 times 58 is 174 grams. Over here then, if we go in pink, how do I actually make that solution? Well, you weigh out 174 grams of salt. What's your next step? You add the salt to a 2-liter volumetric flask, because volumetric flasks have one line on them, and that line will be exactly 2 liters. So what do we have so far? You have a flask. What's in it? Just salt. Add water, about half. Stir to dissolve. Now, what have you got? You've got a bunch of salt dissolved in water. Then what you do is you add water to the line. What do you have in there? You have 174 grams of salt. How much water do you have? You don't actually know, because that 174 grams of salt actually took up some space. So you can't say that you added 2 liters of water. All you can say is that you added enough water to bring it to the 2-liter mark. So what are you left with? 2 liters of solution. You don't know exactly how much water. You don't really care. You just want to add water till it gets to the line. So that's an important difference between the two. So molarity is always moles of solute per liter of solution. and that helps us do all kinds of things. If I tell you you have 3 liters of 1.24 molar solution and you have to do stoichiometry with it, how are you supposed to do stoichiometry with that? Well, you know that molarity is moles over liter. So 1.24 molar is equal to, I don't know how many moles, over 3 liters. And once you know that, you can solve for the number of moles. And so all of a sudden, when you're doing stoichiometry, use molarity to find the number of moles. As soon as you have the number of moles, you're golden. It's just like doing regular stoichiometry. Then you plug it into your balanced equation and solve for the thing you're looking for. The last thing is this weird thing called molality. Now, molality is signified by the letter M, written in italics or written in cursive is what I write. Molality is a little bit different. It's, again, moles of solute divided by, that's a big line, divided by kilograms of solvent. Why the difference? Why not always use moles per liter? Why not? Well, we do use it 90% of the time. Sometimes we need molality because what if the temperature changes? If the temperature changes, you are going to be in trouble because the liters of solution is either going to get bigger or smaller. It will change. So what is a 1 molar solution at 20 degrees Celsius is no longer a 1 molar solution when it gets to 50 degrees Celsius because the volume changes. Anytime you're dealing with a temperature change, we like to use molality because the temperature will have no effect on kilograms and have no effect on mole. Only when we're talking about temperature changes do we ever worry about molality. If you've got those basic molality and molarity, we will actually go through and practice those some in class.